Good morning. Tu me dis que tu sors en dessous. Good morning, sir. Yes, sir. We have not seen you, sir. Oh, okay, sir. Please, sir. Please, sir. Even before coming, let us send the. Okay, I didn't know the time has changed. I hope there's no clash in the system. Oh, you are correct, sir. You are correct. I just send the slide and immediately so that I can load it to the system so that we won't be doing that one when she's coming. Yes, sir. Thank you, sir. Oh, oh, sister. I didn't know you are the one. Thank you very much. That's why yesterday. God bless you mightily. Uh, eh? Yes, yes, yes. Even though it was late, I got here around past 10, but at least I got here safely. Yes, it's not a small thing. I'm grateful. Thank you very much. God bless you. Thank you. Yeah. Definitely now. Yes. You see me. You see me. You see. Oh, God bless you. Yes. Yes. Thank you very much. Yeah. Bye. Mhm. Báwo Hello, báwo ni? I'm fine. How are you doing too? Your voice shows that you have slept and slept. Uh-huh. That shows in your voice now. I'm trying to say, you have not started lectures. It's true. The Even those in year one, they wanted to force chemistry people to start last week. And that's why they're told, because they normally ask them to start the first day of resumption and everything. I just told them, I said, there's no way. I broke, I broke that tradition, and they were not happy. They went and reported me to the deputy vice chancellor. They reported me to the deputy vice chancellor. Huh? I said, there's no way. I didn't allow them to have lectures. So I think so it's today they will start. How was huh? Yes, I got you around 10. Yeah. Coffee for what? What are they doing? Okay. I don't know. I'm not going to ask. I didn't go to the house. Yeah. But just be enjoy yourself until the fireworks. Have the buses have they started working? Because when I was coming, I was surprised. I saw Keke, new Keke on campus. I know you must have entered one of them now. Eh? Just to go and test it. Eh? Okay, does it get to the staff quarters? I saw it even late at night yesterday, around 10 to 11 or thereabout. It was still and that's wonderful. Oh, let me allow you to yawn very well. Now, how was the retreat now? Okay, so what of effect did you see her? Throughout all the days or maybe one of the days? Oh, yes, yes, you are with your people as a coordinator. So, how did your people get the John come? Oh, brother. So, how many of them came now because you were worried that they may not come? Okay. And where were they sleeping? Yes, yes, yes. That's why I said you shouldn't even worry that time. But very good. They have lifted my discipline. Eh? After. Just, just yesterday. They have been rejoicing at the global fire level. So, I miss my traveling here and eh? No, I don't need to be rushing down. I don't need to be rushing down. I can operate from anywhere. I'm not even fully in Onitsha. I mean, the Onitsha has another father, so we're running Onitsha something. I can go anywhere. So doesn't have to be a rushing to Onitsha. So maybe when they get one ready for my flight, so and so. To meet from the university or from it's when we have workshop. Or the workshop we are going to have this year is for Nigeria. It's a day you. So maybe Professor Adelumo is very busy now. So anything for the boys there. I know you are not working up to cook anything. Why? Okay, because you have been eating at the retreat now. So why will you cook? You will eat three. You will eat 3 square meals there, and that was 2 times. Okay, what in the morning you don't normally take anything? Oh yes, because you have to go to you go to your house. I mean to your hostel. Sorry, the lecture for chemistry you have to take off. We discussed it now. Hmm. Them are waiting. How many minutes to? Okay. Um, which of the
Both, because I will start with hydrogen.
okay?
And then, if the time permits, I'll go to another gases.
Yes. So, okay. Achieving this thing in are you going to well maybe not for today because we need some we don't allow the pictures here.
To come post to my this that hey, where you are going to this level?
Because it's hidden from so many people in the university. This way.
It's Wi-Fi. I'm just like me. This when I'm done, I'll have my head.
Yes. Mhm. Thank you. Let me load it in Microsoft, I mean, in the Google form, so that maybe when next you want to make some description or annotation or something like that, you should be able to do that. But maybe not today, because that for that one they have to come about 20 minutes later, so that you use the pen to see that the match is there. Okay, so thank you. So for today, maybe what I will set up is for you to at least do some highlights or some important.
Yes,
yes, but let me just load it in there. Yes. It's time to join. It's time. Sure. The first one is which one is the first? Hydrogen. Yes. Yes. Oh, chemistry of hydrogen. Yes. No. I hope the AC is not too much.
No, sir.
Yes, ma'am. Yes. It's, oh, I forgot to mute this one. You are now on air.
Thank you, sir. Okay.
So always remember.
Okay, sir.
Interest.
Okay, sir. Thank you, sir. Do I go back to my slides from the feedback?
Yeah. So students are coming.
Okay.
This is school.
Okay, yeah, thank you so much. Okay.
You are on.
All right, thank you so much, sir. Nice to meet you. Good morning, everybody. Introduction. DNA. Well, there is currently an issue globally in which people are now checking their DNA to check for various issues. For some, for paternity issues, some for their ancestry. For me, I really didn't understand why they were doing this until I watched a particular episode of a free interview with the star of Scandal. In that particular interview, she was able to talk about the fact that she needed identity. From this, I could decipher that one of the reasons why people now go for this kind of things is to be able to find their identity, characterization, to be able to know where they belong. Now, the DNA is a molecule that serves as an hereditary blueprint. It carries genetic instructions for the development, functioning, growth, and reproduction of all known organisms. But then, in terms of chemistry, when you talk about DNA, you'll be talking about electronic configuration. The electronic configuration of an element gives us the blueprint of its reactivity. From the electronic configuration of the element, you can talk about the group that it belongs. You are able to know the number of shells present for that particular element. And from there, the potential reactivity characterization of that particular element. From the periodic table, we have the organization of these elements in groups and in periods. In these groups, similar elements are put together as families. And these particular groups have same number of valence electrons. Now, having said all that, let's come to the business of today. I am Dr. Ayla Bola, an inorganic chemist, and I'll be taking you through some elements in the periodic table. We are going to start with hydrogen. I have here with me a pictorial representation. You have the symbol hydrogen, atomic number 1, electronic configuration 1s, atomic weight 1.008, and the name is also written there. We also have a pictorial representation of hydrogen. You have the nucleus containing the proton and 1 electron around it. Abundance. Now, hydrogen is the most abundant chemical substance in the universe, especially in stars and giant planets. It is prevalent on Earth in the form of chemical compounds such as hydrocarbons and water. This includes fats, petroleum, sugars, and so on. General properties. Hydrogen is the most abundant element in the universe and the third most abundant element after oxygen and silicon on Earth. It is the simplest element, having electronic configuration of 1s1. It can exist in several forms. The molecular hydrogen ion, NH2, atomic hydrogen, proton, that's the hydride ion, molecular hydrogen ion, and triatomic 2-electron species. Hydrogen has 3 naturally occurring isotopes, each with distinct nuclear compositions. 1, the proton, the protium. In this case, this isotope consists of a single proton and no neutron. Deuterium, D. This isotope contains 1 proton and 1 neutron and is stable. Tritium. This isotope consists of 1 proton and 2 neutrons. Now, protium is the most common isotope of hydrogen. Please bear it in mind that all these isotopes still consist of 1 electron in the outermost shell, and it has only 1 shell. Although these isotopes have essentially identical chemical properties due to their identical electronic configuration, they display significantly different physical properties. This includes their boiling points, their densities, their melting points, and so on. Deuterium and tritium serve important roles as tracers in biological research and in improving drug properties. Basic properties and structure. I guess this is where it gets more interesting. Hydrogen has an electronic configuration of 1s1, meaning it possesses just 1 electron in its valence shell. This simple electron configuration is responsible for hydrogen's extraordinary range of chemical behaviors. If you recall, we discussed about DNA and talking about electronic configuration that gives us the characterization, the behavior of these elements. Being the lightest of all gases, hydrogen's molecular weight is lower than any other gas, giving it the highest velocity and diffusion rate at a given temperature. At room temperature and atmospheric pressure, hydrogen exists as dihydrogen, a colorless, odorless gas with exceptional thermal conductivity. This is dihydrogen. You have 2 electrons forming the covalent bond there. A better description here, you can see the 2 electrons there. 2 atoms, in this case, 2 atoms of hydrogen being bonded to have the dihydrogen. Properties of hydrogen. It is colorless, odorless, sparingly soluble in water. It is not very reactive, since hydrogen bond energy is appreciably high. And this bond has to be broken before the gas enters into a chemical reaction with other elements. Now, my first question comes. Why do you think the hydrogen bond energy is appreciably high? Okay. Why do you think it is appreciably high? I'll give you an hint, or rather, I'll probably even answer my question myself. Now, take a look at this. Go back to our structure here. It has one electron and a proton in the nucleus. Now, it is being bonded. Two electrons, two electrons, two electrons. The mass of an electron is 1/1840, while the mass of a proton is 1. The proton is positively charged and the electron is negatively charged. In that case, since there is no other shell, as seen here, just this only one shell, there is no other shell that is protecting that particular electron. It means that this particular electron will be strongly drawn towards the positively charged proton, which is at the nucleus. In that wise, it is not easy to break that particular bond. Therefore, many important reactions involving hydrogen occur in the presence of catalysts, because there is a requirement of energy to break that hydrogen-hydrogen bond, and in that wise to lower the activation energy, which lowers the activation energy by weakening or breaking the hydrogen-hydrogen bond. For example, we have the Haber process. In the Haber process, hydrogen combines with nitrogen at 700 Kelvin and 200 atmospheric pressure in the presence of an ion catalyst to yield ammonia. That's the equation over here. Reaction with carbon monoxide. This also occurs using copper catalysts to produce methanol. Hydrogenation reactions, which convert unsaturated fatty acids, oil, into saturated analogs, fats, also occurs in the presence of finely divined nickel, palladium, or platinum catalysts. So there's for these reactions to occur, there's requirement of additional energy for the breaking of the hydrogen-hydrogen bond. So in that wise, there's use of catalysts for these reactions. Position in the periodic table. Hydrogen has just one electron in its outermost shell, as depicted before, and therefore it resembles alkali metals. Alkali metals are elements in group 1 in the periodic table. I think I should have one here. Very good. These are alkali metals, from lithium to francium. These are alkali metals. And these group 1 elements have one electron as their valence electron. So hydrogen resembles the alkali. How does it resemble the alkali? It can lose valence electron, which is 1, similar to the alkali metals, to form a univalent cation, like alkali metals. In addition, like group 1 elements, hydrogen is a good reducing agent. Therefore, you can place hydrogen in group 1 of the periodic table. But nevertheless, hydrogen also resembles the halogens, that is, group 17 elements in the periodic table. These include fluorine, chlorine, bromine, and so on. It has a tendency to gain an electron to form halide ions. The hydrogen molecule, like halogen molecules, is diatomic. We have seen that earlier, in which you could see that hydrogen consists of hydrogen molecule consists of 2 atoms. So we say it's diatomic. So is diatomic similar to the halogens? These factors favors the inclusion of hydrogen in group 17 of the periodic table. However, hydrogen differs from alkali metals and halogens in several aspects. One of them being the ionization energy of hydrogen is much higher than that of group 1 elements. The ionization energy is the energy required, the minimum amount of energy required to remove the most loosely bound electron of an atom in the gaseous state. Now, if that minimum energy required is higher than that of any group of any member of the group 1 element, then it's difficult to remove, as we have said, any electron from it. Therefore, the tendency to form univalent cation is much less in comparison to other members of the group of the alkali metals. Similarly, the electron affinity of hydrogen is much lower than that of the halogens to form halide ions. This implies that hydrogen is less electronegative than that of the halogens. That is, its ability to withdraw electrons in a bond. Since it has lower or less electronegativity than that of the halogens, it implies that hydrogen is less electropositive than the alkali metals, as well as less electronegative than the halogens. On this basis, we now treat hydrogen separately without clubbing it together with the alkali metals or the halogens. Therefore, it's placed in the center as shown here, as depicted here. You can see hydrogen is placed at the center of the periodic table. Industrial and environmental importance. Compound formation. It is essential in creating ammonia, hydrogen peroxide, and hydrocarbons. Hydrocarbons contains hydrogen, compounds that contain hydrogens and carbon. So it's important in the formation of all this. In metallurgy, it is used in reducing metal oxides. It's used in fuel and in energy. It's a primary fuel for stars and a fuel clean energy carrier for fuel cells. I'm going to talk more on this. Now, with the dwindling reserves of fossil fuels and rising prices of oil demands and alternative routes, it demands an alternative route to overcome energy crisis. Currently, we are dependent more using petroleum crude oil products for energy currently. One possible route is a fuel economy based on hydrogen. Unlike fossil fuels, geothermal energy or solar energy, hydrogen is not a primary source of energy. It is an energy carrier. On combustion, it produces only water. Hence, the advantage of hydrogen is its virtually pollution-free combustion. It is therefore destined to become a possible fuel of the future. The most practical and feasible method of producing hydrogen is electrolysis of water. In hydrogen-based fuel cells, an aqueous solution of sodium hydroxide or potassium hydroxide is used as an electrolyte. Hydrogen and oxygen are bubbled into the electrolyte. And then the following reaction occurs. At the anode, you have oxygen, water with 4 electrons to give the hydroxyl ion. At the anode, the reaction at the anode, and then the overall reaction. But the more important thing is this. Since water is the only reaction product, fuel cells do not pollute the environment, which is a very important thing now. We want to conserve our climate. We want to conserve our environment. We want to leave a good legacy for the future. So, in this wise, hydrogen is considered as a very good possible or potential fuel for the future, in which more analysis are being carried out towards fulfilling this. Reactivity. Despite the stability of hydrogen, hydrogen still forms many bonds and is present in many different compounds. Atomic hydrogen is reactive. Hydrogen gas bonds in air. It combines with most elements to form hydrides. It reduces metallic oxides to produce the metal in its elemental state. Not only that, it reacts with oxidizing elements, which in turn react spontaneously and violently with chlorine and fluorine to form the corresponding hydrogen halides. The action of hydrogen to unsaturated organic compounds such as alkenes and alkynes is called hydrogenation. Even if the reaction is energetically favorable, it does not occur spontaneously, even at higher temperatures. We have discussed this. In the presence of a catalyst, like finely divided platinum or nickel, the reaction proceeds at room temperature. So the use of catalysts is essential for these reactions. Acid-base chemistry. Hydrogen ion, which have free protons, are the basis of acidity, pH. Flammability. It is highly flammable in air and burns with nearly invisible pale blue flame, producing water. It has two distinct oxidation states, +1, -1, which makes it able to act as, talking about diatomic hydrogen now, it's able to act as both an oxidizing and a reducing agent. Partial positive charge when reacting with more electronegative elements such as halogens or oxygen, and partial negative charge when reacting with more electropositive elements such as the alkali metals. Hydrides. Compounds of hydrogen with less electronegative elements are known as hydrides. Hydrides are classified into three major groups, depending on what element the hydrogen bonds to. You have covalent hydride, ionic hydrides, metallic interstitial hydrides. The metallic hydrides are also known as interstitial hydrides. Ionic hydrides. Ionic hydrides are formed by S-block elements. They are crystalline, non-volatile, they are non-conductive solids. They react with water to produce hydrogen gas. Examples are sodium hydride, lithium hydride, calcium hydride. Covalent hydrides. Covalent hydrides are formed by p-block elements or non-metal. They are generally gases or liquids, have low boiling points. Some of them are often act as weak acids. For example, hydrogen sulfide gas and then HI, hydrogen iodide. Metallic interstitial hydride. These are formed by T, D, or F block elements. I beg your pardon. Hydrogen occupies interstitial sites in this type of hydrides. They often occur as non-stoichiometric compounds. Examples include those that are written there. Uses of hydrides. Hydrides are used as reducing agents. Metal hydrides are used as reducing agents generally. Energy storage in rechargeable batteries, e.g., nickel hydride batteries. They are also used as bases. They are ionic hydrides. They are used as bases and as drying agents. Oh, yeah. That's the end of hydrogen, our lectures on hydrogen. We are going to the next topic group, which is noble gases. Noble gases. Now, noble gases are elements that you find in group 18 in the periodic table, as depicted here in this picture. Have from helium to radium. Noble gases, the electronic configuration as depicted here. You have helium having an atomic number of 2, electronic configuration of 2, and then valency of 0. Neon, symbol Ne, atomic number 10, and electronic configuration 28. This can be written properly. Assignments. I love to give people assignments. Now, kindly write the electronic configuration of the noble gases in the IUPAC fashion. Now, for argon, the number of electrons, the atomic number is 18. Krypton, atomic number 36, Kr for symbol. Now, electronic configuration is written as this, but it can be written better, please. Now, noble gas, physical and atomic properties. For the noble gases, we have helium, neon, argon, krypton, xenon, and radium. You have the boiling points. You can see the boiling points increases down the group from helium to radium. The melting point increases down the group. Solubility increases down the group. Atomic number increases down the group. Atomic radius, radii, increases down the group. Ionization energy. Ionization energy, it reduces down the group. Electronegativity. Electronegativity reduces, does it reduces? It reduces down the group as well. Electronegativity reduces. Yeah, now, electronegativity, there is in this trend, yeah, there is a change there. There is an increase in electronegativity from helium to neon. And from after that, electronegativity reduces down the group, and also at xenon to radium, there is a slight increase in electronegativity. In terms of ionization energy reduces down the group. It reduces down the group. So there's a slight change in the trend there between that of helium and neon and that of xenon and radium in terms of electronegativity. Now, can we suggest reasons? Assignment. Can we suggest reasons for these discrepancies here in terms of trend for the electronegativity of the group 18 elements? Now, this picture is quite interesting. Can you decipher what is wrong here? I've added this picture for one reason. One, to show the presence of the different shells. In the case of neon, neon has 2 shells. In the case of helium, helium has 1, similar to hydrogen. In the case of argon, argon has 3 shells there. So can we spot whatever is the problem here? But in the case of krypton, is krypton, this depiction for krypton, the number of electrons in the outermost shell, and then the penultimate outermost shell, is it correct? Please indicate in the comment section. Names of the noble gases. The noble gases are also known as inert gases. They are also known as rare gases, rare earth gases, group 8, group 0, group 18. And for all this, there are different reasons for them. Assignment number 3. Suggest reasons for these different names used for the noble gases. Reasons why we call them inert gases, why were they called rare earth gases, why are they called accept, what are they accepting now? Okay, group 0 and group 18. Now, occurrence and abundance of the noble gases. All the gases are present in Earth's atmosphere. The abundance in the universe decreases as the atomic number increases. Most of them are often found as monoatomic gases. Helium is the most common element in the universe after hydrogen. All of them can be obtained from here, except helium and radium. The major source of helium is from cryogenic separation of natural gas. Neon, argon, krypton, and xenon are found in air and are obtained by liquefying air and fractional distillation. Radon is a radioactive noble gas. It is produced from radioactive decay of heavier elements including radium, thorium, and uranium. General physical properties. The electronic configuration of helium is 1s2. So you are going to write the electronic configuration for all the other elements using 1s, 2s, 2p, etc., etc. Now, while that of the remaining noble gases is ns2, np8. In the case of neon, neon will be what? Neon will definitely be what? 2s2, 2p6. 2s2, 2p6. For the outermost, the valence shell. So, in other words, the valence shells of this group 18 elements is filled. It's completely filled. These elements have a complete valence shell, and this is responsible for their non-reactive nature. The electron affinity of group 18 elements is 0. Their ionization energies are very high. As a result, atoms of these elements have little tendency to either gain or lose electrons. In their natural states, these elements are colorless, they are odorless, they are tasteless, and they are non-flammable monoatomic gases. They are monoatomic gases, their valence shell is full. They have no, they are satisfied, they are stable. They have no need to look for another electron to come and join them because they are stable, they are satisfied. So they exist more as monoatomic gases. These elements are gases at room temperature and pressure. The only source of attraction between the atoms of a particular noble gas are weak van der Waals forces of attractions, also known as London forces. These increase from helium to radium. The boiling point for helium is 4 degrees Kelvin. It is the lowest of any known substance. The noble gases able to diffuse through materials such as rubber, polyvinyl chloride, and even metals. Helium even diffuses out of glass. Therefore, ordinary glassware is not suitable for cryogenic studies involving the gas in liquid state. General chemical properties. The noble gases are characterized by low reactivity. Like I said, the outermost shell. One thing we said, the electronic configuration gives us information about the characteristics and the properties of these elements. In this case, for noble gases, their valence shell is completely filled. They have filled number of electrons in their valence shell, fully occupied. So they have low boiling points. Their melting and boiling points, which are close to each other, are over a narrow range. Low ionization, very low electronegativity. Low ionization because they're not willing to lose electron. They are filled. They are satisfied. They are stable. Very low electronegativity. It's not hungry like the halogens. We will need one electron to complete their valence shell. They are stable. They have fully filled valence shell. And they are powerful oxidizing agents. The larger atoms are easily distorted or polarized by other charged bodies due to weaker attraction of the nucleus for the electrons in the distant valence shell. Why do you think the larger atoms are easily polarized? From our discussion on the atomic radius and ionization energy, we said the ionization energy does what? It reduces down the group. That is the minimum amount of energy to withdraw the most loosely bound electron in the gaseous state. It reduces, which means that helium has higher energy than that of radium or xenon. If that is the case, if less amount of energy is required to remove electron from xenon compared to that of helium, then they are more easily polarizable than helium. Be that as may, they still have high ionization energies, be that as may. Due to the larger atoms are easily distorted or polarized by other charged bodies due to weaker attraction of nucleus for the electrons in a distant valence shell. Now, the nucleus contains the proton and the neutron. The proton is positively charged, neutrons are neutral. And you have your electrons in the outermost shell. The attraction of the electrons for the lower bottom elements towards the nucleus is reduced compared to that of helium, in which only one shell exists. Therefore, the two electrons are more easily drawn towards the positively charged nucleus. This polarized atom becomes unsymmetrical, though the atom remains electrically neutral. Polarizability of the noble gases increases from helium to radium. We've said that. Now, compounds formation and their reactivity. The compounds form coordination compounds. They form compounds by excitation. They form compounds by induced dipole, and they form compounds using clatrates. They form clatrates. Reactivity. The chemical reactivity of noble gases is largely restricted to krypton, xenon, and radium. Remember, radium is radioactive. This concurs with the decreasing ionization energy, as we have discussed before, and the decreasing energy from pairing the valence electrons or moving down the group. You require more energy. This concurs with decreasing ionization energy and the decreasing energy for the unpairing of the valence electrons or moving down the group. Xenon forms the largest number of compounds known for noble gases. Radium is radioactive and has no stable isotope. This makes it difficult to isolate its compounds. The compounds of xenon invariably involve bonds with fluorine or oxygen or both. Another assignment. Can you suggest reasons why bonds are formed between xenon and fluorine or oxygen? Why? Why is it not forming bonds with alkaline metals like lithium? Why is it forming compounds with fluorine or oxygen? The removal of electron from an atom of xenon by way of ionization or promotion of electron to higher energy levels by the way of excitation is not a one-way process. It has to be communicated by the atoms with which xenon reacts with. Fluorine and oxygen have the highest and second highest electronegativities, respectively, among all other elements. In other words, fluorine and oxygen are highly electronegative. They are the highest, 1 and 2, top number 1, top number 2 elements amongst all the elements in the periodic table. Which means it's more hungry to obtain additional electron compared to any other element. Those two compared to any other element in the periodic table. So they are hungry. They want that electron badly for them to complete their outer shell, for them to have a complete valence shell. Therefore, for someone that is stable, they can still attack it so that they can have a reaction. They assist in the removal of valence electrons of xenon from their ground states. Therefore, xenon prefers to combine with these atoms. Xenon exhibits a range of oxidation states from 2 to 8, that is plus 2 to 8. Reaction with platinum, that is, we are talking about reaction of xenon. Now, xenon reacts with platinum-6 fluoride. When xenon is mixed with red vapors of platinum-6 fluoride, a yellow-colored solid is spontaneously obtained. This undergoes the following stepwise transformation, as depicted here. But not only platinum-6 fluoride. An analogous reaction of xenon occurs with other thermodynamically unstable metal fluorides, such as ruthenium-6 fluoride and rhodium-6 fluoride. However, stable hexafluorides such as uranium-6 and iridium-6 do not react with xenon. Can we suggest reasons for why this is so? Reaction with fluorine. We have talked about its reaction of xenon with platinum 6 fluoride, reaction of xenon with fluorine. Xenon forms 3 fluorides. 1 difluoride, 2 tetrafluorides, 3 hexafluoride with direct reaction with fluorine in carefully controlled stoichiometries. You have the difluoride, stoichiometric ratio 2:1, xenon to fluorine. The tetrafluoride, stoichiometric ratio 1:5, xenon to fluorine. For hexafluorides, you have stoichiometric ratio of 1:20, xenon to fluorine, which means that in this case, fluorine is in excess here. Mind you, xenon is stable. In xenon difluoride, the central atom xenon is sp3d hybridized. It's telling us something. It's telling us about the geometry. The structure may be described as either trigonal pyramid with 3 equatorial positions occupied by lone pairs of electrons. It can also be considered, more precisely, as linear. Now, why is this so? In terms of hybridization, you can consider it as trigonal bipyramidal. But in terms of the number of atoms attached, you can call it as being linear. In xenon tetrafluoride, 2 electrons from the valence shell of xenon are promoted to the 5d orbitals before invoking np3d2 hybridization. Even from this, by default, you have np3d2, 1 plus 3 plus 2 means 6. So you have 6 atoms. Sorry, 6 electrons, 6 hybrid orbitals. You have 6 hybrid orbitals in this case. So if you have 6 hybrid orbitals, you're talking about octahedral geometry. The structure is octahedral with 2 axial positions occupied by lone pairs of electrons. This may be described as square planar. This is in terms of the number of atoms attached to xenon. But in terms of hybridization, it is octahedral. Now, xenon hexafluoride assumes an octahedral geometry. The xenon hexafluoride assumes an octahedral geometry. In fact, in terms of the number of atoms attached, it's still octahedral as well, because there are 6 atoms of fluorine. Noble gas fluorides are powerful oxidizing agents. Their reactivity follows the order neon, helium, argon, krypton, and xenon. Clatrates. We said that these compounds form clatrates. So clatrates are compounds formed by trapping of atoms or molecules in the cavities of a crystalline compound. I think I have an example here. This is encapsulation. The atom or molecule is encapsulated in a cage-like form. There are no chemical bonds between the guest and the host. The guest is the one that is housing the molecule. Sorry, the host is the one that is housing the molecule, while the guest is the molecule in question. So there is no chemical bonds between them. It's like it's encapsulated inside the host species. Only physical attraction manifesting in the form of van der Waals forces of attractions occurs. As an example, argon krypton and xenon form clathrates with crystalline theta quinol. However, helium and neon do not fit into the cavity as a result of their small size. This is just an example of a clathrate. It's not exactly that of a noble gas. Uses. The inertness of the noble gases enhance their applicability. They can be used to shield reactive chemicals from oxygen. They are ionized for use in lamps and lasers. They are used in the preparation of ultra-pure silicon and germanium crystals and other semiconductor materials used in transistors. Their low boiling point and melting point makes them useful as refrigerants in the study of matter at extremely low temperatures. Helium. Helium is used by deep sea divers to prevent oxygen, nitrogen, and carbon dioxide toxicity. Remember, for deep sea divers, they carry their tanks. They can't, because oxygen is dissolved in sea, water, and so on, ocean, sea. Oxygen is dissolved in the water. And for them to breathe at that kind of level, at those levels, they require to carry oxygen tanks with them. Now, this oxygen tanks is mixed with nitrogen and helium. So it prevents oxygen, nitrogen, carbon dioxide, which they breathe out, the toxicity. It is used to dilute oxygen in gas cylinders used by divers in preference to nitrogen because of the low solubility of helium in fluids. If you recall, we said they don't dissolve in fluids readily. Helium does not dissolve in blood. It does not form bubbles or decomposition as nitrogen does because nitrogen is quite soluble in blood. Another assignment. What other reason do you think that helium is added in gas cylinders for divers? Why do you think they say, apart from the fact that it does not dissolve in blood, why do you think they still had helium in gas cylinders for divers? Helium is used in weather balloons and to fill air ships. It's used as flow gas in liquid chromatography. It is used in cryoscopy as a result of low boiling points. Neon is used in neon discharge tubes, while argon is used to fuel electric light bulbs, fluorescent lamps, and to increase efficiency and life of bulbs. Argon is also used to provide an inert atmosphere for metallurgical processes such as welding of stainless steel. Xenon is used as an anesthetic, though it is costly. It is readily eliminated from the body. On the other hand, radon is only used in radiotherapy in the treatment of cancer. However, it is quite toxic, so very little amount is required. That comes to the end of our lecture today. Do you have questions or answers to any of our questions, please? Why do we do this? Okay, good. Assignment. You don't like assignments. So what is the assignment, please? Which slide is she using, please? She has not released the slides. Are we marking attendance? More. It is CHM. She's using compile slide page 160. Fourth assignment. Not with alkaline metals like lithium. Good. Please, who had the assignment she just mentioned now? Why do you have helium for what? But despite it doesn't mix with blood. Is it that's the first assignment or what? Ah, thank you. You're welcome. Why do you had helium to gas tanks for divers, not weather divers, weathers, helium balls, if you weather balloons, those ones. You have those weather balloons, they use helium. Even they also use helium in balloons for creative birthday balloons too. They had helium for birthday balloons. But for divers, sea divers, ocean divers, they put tanks at the back, gas tanks. They put helium, they put nitrogen, oxygen. Helium is added as a gas used by divers, apart from the ones mentioned. Yeah, another reason why it is added. We have said that because it does not dissolve in the blood. It does not dissolve in the blood, unlike nitrogen. Why do you think, for one thing, if nitrogen dissolves in the blood, you only inhale oxygen, you exhale carbon dioxide. If you have nitrogen, enough nitrogen in your system, my dear, the person has gone to the other side. So do we have other reasons why we have had helium? Thank you. You're welcome. Thank you so much. Thank you. I appreciate that. I love your look. Thank you. Code for attendance. Thank you. You're welcome. Thank you. I'm waiting there. Your call. It's HM 102. Can someone send all the assignments so far she has given? Okay. It's an interesting class. Please, which are we getting the slides? The slides will be available for you, please. The slides will naturally be available. Technology, yeah, I agree. Please, oh, thank you so much. It's an interesting class. Please, when are we getting the slides, ma'am? Yes, you'll be getting the slides, please, naturally. And you are welcome. Inorganic chemistry is very interesting. Child, it's clashing with I believe, I am not sure, this can be recorded and you can check it later. The slides also be given to you. The slides are well done so that even without you attending the classes, I believe you can handle things. What is the assignment, ma? Please. Okay, we'll see that. Please, ma'am, do we have any other CHM class today? Oh, jigby, jigby. There's no other class. I don't want to take the place of the coordinator. That's why I'm being her. So I think we've been told we don't have another class today. Thanks, ma. The class was really effective. Thank you. Another reason why helium is added to the gas used by divers, apart from the one mentioned, yes, I appreciate your answer for that. We mentioned that it's to avoid toxicity and also because it does not dissolve in blood. But there are other reasons too, because it's not just one thing. Let's get the CHM 102 started. Interesting. It's interesting. Open up your mind. Please, ma, can you give us the exact slides? Definitely. I'd like to be having physical class today. Nope. See, if it's online, it's just once. No, we started online now. Thank you, Falaye. Oh, thank you so much. I appreciate it. You can watch the video later. So I'm told too. Guys, stop commenting. We are done with the class. Thank you, ma. Thank you so much. Thank you so much. Fale, Salome, thank you. Elizabeth, Olademoni, Olademoni. Oh, beautiful. Thank you. Thank you. I appreciate it. This inorganic chemistry is fun. It's very interesting. Practical chemistry is life, please. Oh, thank you. Thank you. Jeremiah David, thank you. Good morning, ma. Good morning. Attendance code, well, sorry, I don't. They'll send it in next class, please. Please, is there any attendance code? They said they'll send it in next class. Is there any code for attendance, ma? We'll send in next class. Attendance code, please. We send next class. You made the class intriguing. Thank you, ma. And God bless. Thank you so much. I appreciate it. I think that should be the last chat. This is my first time of doing something, so I think please you should consider physical class too. Data is expensive. Wow.
If you want to be doing it, have to have hybrid. Those who don't have data, you can go to some classes.
Yes, in the future. Oh.
Make it hybrid. But they will not see you there. It's a screen, they will still see.
Okay, sir. Thank you so much. This was. Can you imagine? Someone said fear is worse, which is true. The transport fare is worse. It's worse, honestly. Relative to data, yes, it's worse.
With how much data now we can put this on?
Many, yes, sir. Thank you for replying to our comments. Thank you. Wow, this is so interactive. Yeah, it is a very good class, ma, but we still need slides. Yes, you'll be giving the slides. The slides are made for you. They are easy and straightforward to the point for you to handle. What are the assignments? Don't worry, we'll pick them up one after the other. Thank you so much for the classmates. Really interactive. Thank you. The third assignment, please. Thank you so much, ma. That's so interesting. Thank you so much. I think you can get the assignments from the class. Thank you so much, Queen. Well, I think at this rate, thank you so much, everybody. If you have any questions, please do let us know. When is the next batch? I think that should be next tomorrow. That will depend on the coordinator, and that will be passed to you. Please, I need to get this. You will definitely get the slides. Thank you. Thank you. Yes, sir. Okay, so tomorrow there should be another class. Okay. All right. So best of luck. Any questions, please let us know. And I said the slides are straightforward, easy to read, and not too much. Thank you, everybody. Thank you so much, sir.
Thank you.
So tomorrow,
You
what
found a
time?
wonderful class.
Thank you. But it has not.
You know, the class tomorrow based on our semester. People they are trying to follow, if they're following maybe this last semester, This is like
Okay. This is 102, that is 101. This is 102, that is 101.
this is changing.
I will tell you. So I can collect your phone number, so I can also be contact. Don't send me all this technology. Okay, sir. 0806
84
844
3742.
3742.
Abiodun Akinwale.
Akin.
Abiodun Akinwale.
So I've tried to flash.
It's okay, man. So, they have the privilege of going over